FMO3 is flow measurement apparatus. So these are different apparatus that we put in pipe systems to monitor the flow rate or to measure the flow rate. So you might not see all of them in one system, but in our experiment or in the lab, we will try to put all these three together in one very small pipe system just to show how we determine the flow rates using these three things, three devices. They are put inside the pipe. So this is the Venturi, or they are integral to the pipe system. So this is called the Venturi meter. So you can see you have this holes here and this one here. This is some connected to something to measure the height of water. And this is a longer diameter and somewhere is constricted here, smaller diameter here. You can see the change in cross section here. The other meter or measuring device is called the orifice meter. So in here you have something like this. So it's an orifice meter is something where the cross section of the whole pipe is gets very small or constricted. So something like this. So this is the original diameter of the pipe. If you put the orifice, it will be constricted like this. So in this area, you would have what we call a vena contracta, where the flow area becomes really very small. So this is called the orifice meter. And the other one is called a rotameter. So rotameter is you have this cylinder here, something like a cylinder, and it's tapered. And when I say tapered, it means that the cross-sectional area increases as you go higher here. So something like this. So here in the bottom, the cross-sectional area of the pipe is smaller, and here it's bigger. So what happens here is that when you increase the flow, this float here, there is a float here. When the flow rate is low, it would stay at the lower level. But when you increase the flow, it would also stay here in the area where it is wider. Okay. And the position of that float determines the flow in the pipe system. So here how it looks like in the lab. So the Venturi meter is somewhere here. Um, the Venturi meter, I think, is somewhere here in this area. Venturi meter is here, the orifice meter here, and the rotometer is somewhere here. Okay. And these are connected to this manometer, these tubes over here. Okay. So now this experiment, I think, has there are two objectives, not really two parts, but two objectives, if I'm not mistaken. So one is to demonstrate how the flow rate is measured using these devices, and the other is calculating the head loss. Now you have to go through the lab manual for the derivation of all the equations because they are all in there. But to do that, you would have to be able to study first the energy theorem, which we will be discussing in maybe in 2 or 3 weeks from now. Okay, so I have equations that I put here as an example, but they're already the derived one. The derivation is quite lengthy, and like I said, you can follow the manual. So for example, for the Venturi meter, this is the equation here. So let me just explain a little bit about this one. AB here is just a cross-sectional area of this one. So all these dimensions are given, actually. You can find them in the manual, but you can also find this in um, the device itself in the lab. So they are marked there. So you need those values. So please take note of them. You need them in your computations. So A is the cross-sectional area at section B. Sorry, section B is somewhere here, the one with 16 millimeters. Uh, A A is the cross-sectional area at point A, this one with a 26 diameter cross-sectional area. 2G is a constant, and then you have HA and HB. So what are these HA and HB? So this is the height of water connected to A and to B. So this is how it looks like here. This is where you will measure HA and HB. So I think this is the A. So if this is A cube, you would have to look here, the height of water over here. And then what is the other one? B. So you have to trace B again. So if I might be mistaken, so you have to look in the lab because all of them are labeled. So there is a label here, A, B, C, D, E, F, G, so that you can see where exactly to look. So that can be read, sorry, in here in these columns here. So that value and that value, and this can be computed, and that's how you get your Q. For the orifice meter, it's the same. You also have the cross-sectional areas at different points, and then you also have the height of water at columns E and F over here. And then this C is a coefficient for this orifice, and it is given, and you just have to find the value in the manual because that is given, okay? And that's how you measure flow. The other thing you need to derive, I think, in this experiment is the head loss. Again, you go through the manual because the derivation is in there. So the head loss is based on flow rates, I think, or in the velocities. Velocity and flow rate are related by the equation, by the continuity equation. Okay, so that continuity equation, you will know that in the lecture. Oh, sorry, not yet finished. So this is the rotameter. So for the rotameter, like I said, so you will be able to graph the relationship between the flow and the height of the float. So when you increase the flow rate, so this is just an example of that curve. So when you increase the flow rate, the position of that float also uh, increases. So from this line that you make out of that, you can have a trend line, or you can have like the relationship. So that at any height that you have your rotometer, then you can just predict the flow rate just by looking at the height here and the corresponding point in the line.